in this example, it says you are standing at the top of a ladder leaning against a wall. As the ladder falls down the wall at a rate of 4 feet per second, your friend is standing 6 feet from the wall. How fast is the ladder moving when it hits your friend? So a couple things that we know that the ladder is falling. And what we want to do is kind of think about, like, how would a ladder fall if it's leaning up against, a wall? So if we had a nice little wall, and then, here's your ladder. If it's falling down, obviously you're going to have this distance, vertical distance is going to be changing, right, which is going to be falling. But then also we're going to have this distance against the ground here. That's actually going to be moving out as well. Would you guys agree? Right? So we kind of have like two distance changes that are going on. Now the other thing that's kind of important is looking at this, and we see that this is a triangle. And whenever we see a triangle, we want to maybe make sure we have some certain characteristics, because in pre-calculus and in geometry, there was a really, really special type of triangle that allowed us to do a lot of different things. Does anybody know what that type of special triangle is? A right triangle. And a right triangle, the reason why right triangle is so helpful is not only can we now, if we have a right triangle, we can apply the Pythagorean Theorem, right? That is only can be applied when you have a right triangle. We can do the 6 trigonometric functions, right? That's only allowed. We can only apply those with the 6 trigonometric function or with a right triangle. And then also we have special right triangles, 45, 45, 90, 30, 60, 90 triangles. Those we can find the given side lengths without really having to do much math. And that's obviously the basis off the unit circle and so on and so forth. All right, so now I've kind of just drawn like a little picture, and obviously we have this little guy here, whatever else. I feel like there's something else that I have. Uh-oh, you're standing at the top of a, sorry about that, I did forget to write that in, 10-foot ladder. Let me just make sure I copied that down. So you have a 10-foot ladder. You are falling at 4 feet per minute. That is correct. And we're looking at away from the wall. All right, perfect. So a couple things is let's start to get some things down. All right. So if we want to look at this, we know that down the wall is 4 feet per second. So we know that that is a rate, right? That is a derivative, right? That is the rate that something's falling, correct? This is 6 feet. That is a distance, OK? So that's how far your friend is. You're right up here. That is how far your friend is, right? That's a distance. And then what they're asking is how fast is the ladder moving when it hits your friend? So they're asking, are they asking for a distance or are they asking for a rate? Rate, right? OK. So now that we've understood that we're asking for a rate and we're given a rate, that means we need to find the derivative of something, right? Yes? So we got to look at this picture and say, all right, well, what equation can we create based on the information we have that we can find the derivative of? And we notice that there's basically two things that are going on. We have a distance here that's changing. We have a distance here that's changing. Now we have a distance here that is not changing, right? Z equals 10 feet. However, that is at least a distance. And we can write a relationship with these distances, correct? Yes? So if we write the relationship with these distances, we could say, x squared plus y squared equals z squared. I know z squared is going to be equal to 10 for a second, but I just want you guys to see that we can write this relationship. We could also do tangent, sine, cosine, theta. But again, guys, you got to think in your head. Are we talking anything about a change of an angle? Do we care about a change of an angle? Do we care about the change of an angle with respect to time, right? The d theta dt. No. So we don't really want to use that relationship. We are talking about changing of distances, though, right? Do you guys agree? So that would be helpful for us. All right, so I would say definitely number one, guys, is to obviously understand the information you're given, underline, circle it, draw some sort of picture, OK? That's going to help you at least just visualize, represent. That's not obviously necessary, but especially for some of the problems that get confusing or when you get stuck, going back to a picture is kind of helpful. And then I think and the next thing we want to do is just start writing down some of the relationships we have. Because obviously, guys, if we're talking about a rate, we got to find the derivative of something. You can't just say, oh, we're going to plug in the rate of something. Like, we don't have an equation. So we find a relationship based on our figure. We create that. Now let's go ahead and find dt of our relationship. Or sorry, d over dt. Did I write that? No, OK. Right? So now what we want to do is find the derivative of our now we want to find the derivative of our relationship with respect to time. Because kind of like on our warm-up, we know that if we're doing the distance with respect to time, that is like our rates, right? The miles per hour, the feet per second. In this case, it's the feet per minute, right? So when we go ahead and find the derivative here, we get 2x dx dt plus 2y dy dt equals 2z dz dt. And again, guys, you could label this any way you want to, right? You guys could use A, B's, and C's if you wanted to. All right, so now I've created this. Now I've created this second equation, which represents my rates, and that's awesome because now I can plug in stuff that I know. All right. So again, we're trying to find. So we got to go back to the question. I think this is the biggest mistake a lot of people make when I see doing word problems, is they'll answer a math problem or they'll answer the word problem, but it's not for what we're looking for. Like they'll answer something else, but it's not what the question is asking for. So again, we're trying to find how fast is the ladder moving when it hits your friend. So basically, we're trying to find dx dt when x is equal to, anybody? 6. That's what we're basically trying to find. We're trying to find the rate of change of x, how fast that ladder is moving, when the ladder's 6 feet away from the wall, because that's where your friend is at, 6 feet away. Right? So that's what we're trying to find. So I'm going to keep that in the back of my head now and trying to say, all right, so I know I don't have dx dt. That's what I'm going to solve for. So do we know x, obviously, that we're trying to solve for? Yeah, that's like evaluating. So that's going to be 2 times 6 dx dt plus 2y. Now, 2y is, we do not, what did I come in for my? So in my y, we see that that's an unknown, right? Do you guys agree? We don't know how tall the ladder is. So then we got to kind of go back to the drawing board and say, all right, well, at 6, we have 6, 10. Can we figure out what y is? And then what's nice is because, again, we have this beautiful right triangle, we know that all we need to do is apply Pythagorean theorem. So we could say 100, 10 squared equals 6 squared plus y squared. 100 equals 36 plus y squared. Hopefully you guys can do the math with me. Y squared equals 64. Square root, y equals plus or minus 8. But obviously we know that negative 8 doesn't really make sense in the context of this problem, right? But I'm still going to actually show you, still going to include plus or minus 8. Because sometimes in the context of the problem, negative 8 actually would, or a negative value would make sense, right? If we're talking about not so much like, if we're talking about like direction, negative 8 direction is different than positive 8 direction, right? So we're going to get to those problems. But for right now, we're talking about the height of a ladder. The height of a ladder doesn't make sense in the context of our problem to be negative 8. It makes sense for it to be 8. So that's going to be 8 in this case. So then I have 2 times 8. dy dt is again a rate, and that's moving at 4 feet per second. But if we look at this, guys, where is it moving? Is it going up or is it going down? Down. So we got to understand that since this is moving down, we know that it's going to be negative. So you could use the units, but we know what exactly I'm solving, so I'm just going to keep the units out just to simplify everything. And then the last thing, in this case is 2z times dz dt. So we could do 2 times 0. But then in this case, guys, if you look at this, What's dz dt? How much is this ladder changing? I'm sorry, z is 10. Sorry. Is the length of the ladder changing? No, right? So that's going to be 0. So anytime you guys have a fixed length, we could have like skipped along this much faster if we wanted to. But anytime you guys have a fixed length, you know that the length is not changing, right? Yes?
Can you tell me how you got -4?
So we have the rate, right? But the rate is 4 feet per second. But that is for the graph falling. OK? So that means we're going to include a quantity of it falling, going down, being negative. OK? All right, so then that equals 0. So therefore, we have 12 dx dt. And therefore, that's going to be -8. So that's going to be minus 64 equals 0. And what do I have? And then we'll just solve. And then obviously, we're just trying to find dx dt at x equals 6, which I've already plugged that in. So then I'll just add 64. 12 dx dt equals 64 over 12, which dx dt is equal to 16 over 3. And then just remember, do not forget about the units. We could have included the units up there in the front, but just remember to include that. Because if you don't include, obviously, that, you're not putting a quantity on the values. So therefore, it's going to be completely different.